Okay, so we're going to do 2D vectors first. 2D means two-dimensional, right there. And we will get into 3D vectors right after. So I am going to do vectors today, and we're going to do vectors for like the first week and a half or so. But I do want to lay out in 25 words or less, maybe a little bit more than 25 words, what Calculus 3 is going to cover. Like, what's the semester going to entail? I bet you're interested in hearing that, aren't you? So here it is. Calculus 3 is going to be Calculus 1 all over again, but in 3 dimensions instead of 2 dimensions. Isn't that great? Yeah, that's what we're doing. And here's some even better news for you. Remember all those sequences and series that you did in Calculus 2? We're not going to do any of those in this class. Isn't that great? Now, that's not to say that you're not going to use those in another class. So if you're taking differential equations, they will be doing series in that class. And I've taught that class. It's a wonderful class. So that material that you did learn in Calculus 2 will be relevant. So don't completely forget it if you want to do well in differential equations. So in a nutshell, here are 2 things that you did in Calculus 1 that we're going to do in Calculus 3. The first thing is, if you recall in Calculus 1, if you were given, say, the graph of a function, say y equals f of x, one of the big things you did back in Calc 1 is they would pick a point, say right here, when x is, I'm just going to make something up, say some number c, and they would go, hey, what's the slope of the tangent line at that point? And in Calc 1, I hope you remember, oh yeah, we did that. And what was the slope of this tangent line? Does anybody remember how to get a slope of a tangent line to the graph of y equals f of x? If you don't, that's okay, but
Derivative?
yes, thank you. Yeah, the derivative. So the slope would be f prime of x, or in this case, f prime of c, because we want it right there when x is equal to c. So in Calculus 3, you're going to be doing a similar thing. Really? Yeah. We're going to be working in 3D. So you have 3 coordinate axes instead of just 2. And we're going to be looking at the graph of a surface instead of a curve. So you'll be having some surface. I'll just graph this is like a capping surface here. If you can imagine, this is 3D. And then we can pick a point. You can think of that as being a mountaintop, if that helps. I'll pick a point on the mountain, like right there. And let's say you're a skier and you're going to ski down the mountain. What's the slope right there? We're going to go over how to do that here in Calculus 3. Pretty cool, huh? The second thing that you learned in Calculus 1, just as a reminder, is, again, you'd have some graph of y equals f of x. And then do you guys remember that back in that day, when you took your Calc 1 class, they would ask you to find the area under the curve? Calculus 1. Does anybody remember how you would find the area under that curve?
By the integral.
Good. You'd integrate from what to what?
From a to b.
Good. And then what would you put here in the integrand?
Your equation, and then you end with dx or dy or something.
Yeah, in this case dx, because we've got on the x. Yeah, so your area was an integral. So what did you do in Calc 1 in a nutshell? You did derivatives and you did integrals, but you were working in 2 dimensions. Here in Calc 3, we're going to do derivatives in a different way, of course. And then instead of area, we would find the volume of this solid that would have the capping surface of this pink thing. So you're going to be looking at finding a volume, and it's going to involve a double integral or a triple integral. Don't worry about that right now. That's not for like 3 months away. And that's basically what Calculus 3 will be about, is doing Calculus 1 all over again in 3 dimensions. Exciting stuff. So we're going to look at vectors in the plane. So this word plane is not an airplane. So anytime you hear the word plane from now on in this Calculus 3 course, think 2 dimensions. And you'll see that in the textbook. You'll see it on some of the homeworks and quiz problems. They'll say, oh, you know, check out these vectors in the plane. And immediately I want you to think, ooh, 2 dimensions. 2 dimensions. Okay, now let's get some definitions out of the way, and then we'll have some fun and play with vectors. Okay, so introductory definitions. Scalar quantities. What the heck is a scalar quantity? You may have heard the word scalar before. Scalar quantities are physical quantities that can be characterized by a, and write this down, single real number. That's right, just a single real number. That's called a scalar. What's some examples of scalars? Well, the length of something is a scalar. Like I'm on a table right here. It's a card table. It's kind of cheesy. But like, what would be the length of one of the sides of this table? You know, I don't know, probably looks to me like it's 3 feet. The 3 is a scalar. It's a pure number. Area is a scalar example. Volume would be another scalar example. And there are many, many more. Vector quantities. Vector quantities are quantities that involve both. So that's going to be 2 things here. So write these down. Number 1, a direction. And number 2, magnitude. Now, magnitude is kind of a weird word. It's a fancy word for length, but it may not always mean length if you're working with vectors that are in 4 dimensions or 5 dimensions or 20 dimensions. Now, in this course, we're going to limit ourselves to 3 dimensions, okay? On occasion, I might talk about 4 dimensions. But if you're taking linear algebra, that's a fun course. They work in any dimension. Yeah, cool. Okay, well, what are some examples of vectors? And if you've already taken physics, good for you, because you probably know what the answers are here. Force is a vector quantity. Velocity is a force, so that is an example of it. Acceleration. Okay, fill those blanks in and let's keep going. So now let's talk about how you represent a vector. We're going to be drawing pictures next. So get ready for some pictures of like, what does a vector look like? So a directed line segment. A directed line segment is used to represent a vector. Really? Like, what do you mean? Well, here's a picture of a vector right here on your course reader and lecture notes. It has a point here labeled A, and then it has another point over here labeled B. The point B has an arrow there. Only one arrow, not both points having an arrow, just one. So it's a line segment that's directed, so it has a direction. This vector happens to be pointing where the arrow is pointing, so that's the direction. Some more vocabulary. The initial point is A. That's the initial point. That's the point that doesn't have an arrow on it. It is sometimes called the tail, aka also known as the tail. The other point, B, is known as the terminal point. And yes, I'm going to use these phrases in the future, so know which is which, otherwise you'll get really confused. And sometimes they call that the tip. So the tip is where the arrow is. Okay? Now, this vector that you're seeing here, this picture, does have a direction. It looks like it's pointing a little bit to the right and up. And magnitude is its length. And we'll talk a little bit more about this in a moment, but I just want you to get that the magnitude would be how long that vector is, how many units, the length. So now let's do some notation, and notation is important. So for example, when you do quiz 1 this Sunday and you turn in your handwritten work, I am going to be looking very carefully that you have honor the vector notation that we use in this course. And when you first start out, you may be a little bit remiss in doing it perfectly, and I'm going to be real nice. I won't take off too many points or anything. But as the semester progresses, if you continue to not honor the correct symbol language that we use, symbolic language here in math with the correct symbology, and then you might lose a few more points. So we don't want that to happen, right? So let's look at notation. So the notation for the vector above using the directed line segment notation is AB, and there's a little arrow on the top. So if I were to handwrite it, it would look like that. Note that the order matters. AB is very different from the vector BA, because BA would point in the opposite direction. Okay, the only thing that AB would have in common with the vector BA would be their length. That would be the same, but not the direction. Now, when you're reading your text or a quiz or your homework, they're going to denote vectors not with a little arrow on the top. They're going to use boldface. So this is an example of text right here. Lowercase letters are also very common in denoting vectors. So lowercase v, and it's in bold. So there's no arrow on the top, but that'll mean vectors. Now, it's very customary to name vectors with lowercase letters. Okay, well, what about here? You're using uppercase. Well, I'm not naming the vector there. I'm using the points, the initial and terminal points, to help me name the vector. In that case, typically points are labeled with uppercase letters. I'm just telling you the tradition, okay? Now, when you handwrite your stuff, and that's going to be you when you upload your quizzes and exams, you're going to make sure that you're not going to be able to use boldface, because I don't want to look around and see, you have to like use a thick pen or something. You'll just write the lowercase v and you'll put a little arrow on the top like this or like this. You can do it like with a half arrow. I'll be okay with that. Either one of those I'm okay with on your exams and quizzes. And that means the vector v. Yeah. Now here's the weird fact. Anytime you're given a single vector like v, it actually represents infinity vectors. What do you mean? This vector right here is just one vector. How could that one vector represent infinity vectors? It does. It represents every single vector that has that exact magnitude, length, and any vector that shares the direction that it's pointing, which is kind of upwards and to the right. And you may think that this key weird fact has no bearing on you, but today you're going to see that it will matter. And in physics, it matters too. And the reason why is it means that anytime we're given a vector, as long as we maintain its integrity, how long it is and where it's pointing, you can move it around anywhere you need to help you out. And that's cool. Because sometimes if you're trying to work with a vector diagram and you've got more than one vector in your picture, you can move your vectors around as long as when you translate them, they stay the same length and they stay pointing in the same direction. Very, very powerful fact. Super powerful. Okay. So, any questions so far?
Nope.
Okay, we're all good. Yay. Okay. Let's talk about some more definitions. I know there's a lot of definitions to start us off. We can't do a lot of fun until we lay down all the groundwork so we can play a good game, right? You got to know the ground rules for the game before you play. Standard position. What does that mean when you have standard position of a vector? The standard position means the initial point, that's the point that doesn't have an arrow on it, is located at the blank. At the blank? What's that? And that is at the origin. So if your vector is in standard position, somebody has moved it around so the initial point is there at the origin. And that's really useful a lot of times when your vector is located in standard position. Does it have to be? No, but it's easier to work with, as we'll soon find out. All right, now let's talk about the definition of component form for a vector in the plane. So remember, plane means not an airplane, but it means 2D. If a vector v is in standard position, then the vector v can be written like that. What? Okay, you've got these angular brackets like this, and you're going to be drawing angular brackets on your handwritten work, and then two numbers separated by a comma inside of the angular brackets. Now those two numbers, they're just going to be pure numbers, are known as the, quote, scalar components of the vector v. And remember, we just talked about what a scalar is. A scalar is a pure real number. So the numbers that you see inside your angular brackets are just pure real numbers, delimited by a comma. Okay. And this is known as component form. I love component form. It's my personal preference. There is another way to denote a vector, but we're not going to do that right now. I'm hoping we can get to it today. We'll see about the time. Okay, and the other way is the way our physics brethren like to use better. So if you have a physics textbook already, it's very rare that they use component form, which is unfortunate. You'll see why I'm not a big fan of the alternative form sometime this week, but I can't tell you yet. Hang in there. The zero vector, is there such a thing? We denote it with the number 0 with a little arrow on top. That's to distinguish it from the scalar 0. Those are two different things. The vector 0 looks like that. If you're going to denote the vector zero vector in component form, you'll use those angular brackets and then put 0, 0, because the scalar components for the zero vector are zeros. Yep. Now, what do you think is the magnitude of the zero vector? And what would it even look like? It'll look like just a dot. So the zero vector, if you draw a picture of it, it doesn't look like a directed line segment because it has 0 magnitude. It's 0 length. So I know it kind of looks funny. A zero vector just looks like a dot. Well, what about the arrow? I thought you said that a vector looks like a directed line segment. You know, it's got an initial point and another point with an arrow. Yes, it's true. Other non-zero vectors look like that, but the zero vector is a dot. So what is its direction? And don't say 0. I know this is weird. It actually is assumed to point everywhere. It points in all directions. That's strange. I know. I don't make this stuff up, folks. I just report it. Yeah, I know. Okay, let's look at how to find the magnitude. Super easy because it's just the result of the Pythagorean theorem. You've heard of the Pythagorean theorem, right? So if somebody gives you a vector in component form, then the magnitude, which is sometimes called the length, is denoted with double bars on either side of the vector. Although Briggs, your textbook, uses single bars, which I'm not a big fan of because some people think that looks like absolute value, and magnitude is not absolute value. So I personally am not going to be using the single bars in lecture, and I really am hoping you'll warm my heart if in your handwritten work you use double bars also. Different textbooks use different notation, but I'm old school and I learned with the double bars. I prefer it. Okay, so how do you get your magnitude? You simply take the square root of the sum of the squares of your scalar components. And we're going to do some examples here in a moment with actual numbers, so don't worry. Okay, now, there is a difference between a geometric vector and an algebraic vector. Well, what is the difference? I'm going to get to it in a moment with the next example. So don't worry, we're coming there. So we're going to do a lot in this next example. Are you ready? because it'll be similar to what I'll put on a quiz this coming weekend. And it's easy, you'll love it. Suppose somebody gave you the initial point of your vector and they said, oh, it's point P, X1, Y1. You know, so let's just say, I'm just going to draw something here. Here's P, X1, Y1, fine. And way over here is Q with some other coordinates, X2, Y2, fine. Okay, let's say somebody wanted you to find the vector PQ. So if I draw PQ, the terminal point has the arrow on it. There's the vector PQ right there. How would you put this vector into standard position? So what does that mean? It means you're going to take this vector PQ and translate it so that you move it where you maintain its integrity. And when I say maintain its integrity, what that means is you still want it pointing in the same direction and you still want it to have the same magnitude. So I'm going to say, if I move it, your PQ, where the P is located here at 0, 0, and the Q is over here, what would be the new coordinates? We already know what the new coordinates of P are. It's obvious, 0, 0. But what are the new coordinates for the Q? What are his coordinates? Because he got moved. Well, the formulas are right here. Okay, X can be found by taking the difference of the X coordinates of P and Q, and order matters. You want to do terminal minus initial. So the terminal X coordinate minus the initial, and then the new Y coordinate is terminal minus initial. Now the vector PQ, if you're going to denote it in component form, you use these angular brackets, and the X and Y, which you just found with these formulas, which are the same new coordinates of Q, are the scalar components of PQ. Okay, so we're going to do a full-blown example right now with all the new notation and these new formulas we just learned and everything. And hopefully after I get done with this example, some of the fog will lift for you. Yeah, check it out. So A, let's graph it. 8, negative 3. It's right about there. Here's the point 8, negative 3 on this graph, and we'll call him A. And then B is the point 4, 5. 4, 5, right there. Here's B. And they want us to give the component form of AB. So the vector AB looks like this. And it is known as the geometric vector. Write this down, it'll become clear in a moment. So that's the vector AB. And it looks like it's kind of pointing up and to the left a little bit. Fine. Okay. So in letter B, they want us to find the magnitude, but I don't want to find the magnitude just yet. Well, why not? Because I want to do another step first. What I'd like to do is I want to translate this vector so it is in standard position. What does that mean? That means that A is going to get moved to 0, 0 by default. We're going to move them over there. That's the new A position, because the standard position, the initial point, is located at the 0, 0. Now, where is B going to go? You know, when we move him, well, he's going to be somewhere out here, but I want to know exactly. Don't eyeball it and guess. So B, his new coordinates are, if you follow the formula we just said, his new X is going to be his old X minus the initial point's X coordinate, which is negative 4. And then the Y coordinate will be found by taking B's Y coordinate, which is a 5, and subtracting A's Y coordinate, which was a negative 3. But 5 minus a negative 3 is 8. So the new coordinates for B, when you move him, are going to be negative 4, 8. So if I graph that, that looks like it's going to be, where the heck is it? Like right there. Negative 4, 8 is the new B. And there's our vector. Ooh, okay. Notice that this new vector is now in standard position. We call this standard position when the initial point is located at 0, 0. And it's also known as an algebraic vector. It's algebraic once you've moved it over into the standard position, as opposed to being a geometric vector somewhere, located just sort of out there, but not in standard position. Now, how do you denote AB now? Because now we can do letter A. I'm going to use angular brackets, and you're going to use these new coordinates that you found for B, but you're going to put them inside angular brackets. So this right here, AB in component form, you got the angular brackets, and then the scalar components are -4 and +8. Okay, and now we can find the magnitude. So for letter B, we want the magnitude of AB, and that is going to be the square root of the sum of the squares of the components. And anytime you square a negative, I hope you remember it's positive. So you don't even have to put -4 squared. You could have just put 4 squared, right? So what does this end up being? So I'm going to ask you guys a question. True or false? Is it legal to do this as my next step?
No, that's
No.
illegal.
Good. Yeah, you can't do that. That's not mathematically correct. So don't do that. Although I do see some students when they get nervous on a test, they do silly mistakes like that. So that was false. Okay, you're not allowed to distribute a radical over a sum. Oops. What happened there? Oh, sometimes okay. So this is instead, you're going to actually add 16 and 64 together, and I get 80. I'm going to take 1 point away from you if you leave it as square root of 80. Well, how come? MyLab Math will probably give you full credit, although it probably depends. The reason why I would take off 1 point for this problem is because 80 has some factors that are perfect squares. You can simplify this radical just a little bit. So what do you mean? Well, 80 can be written as 16 times 5. Yeah. And since square root of 16 is 4, you can simplify this radical. So there's the magnitude, 4 square root of 5. And please note that magnitude is a scalar. That's right, because it's a length. So it's a scalar quantity. So we're done with letter B, and that is the length of the vector AB. And in part C, they wanted us to sketch both the geometric and algebraic vectors on the same graph, but I claim I already did. Aha! And we're done with example 1. Let's move on to equality of vectors, shall we?
Professor, I just have one question. So on the component form, we wrote the new numbers that we took when we changed the B. So -4 and 8.
Mm-hmm.
So based on the definition that you just gave us, is it always going to be that case?
Mm-hmm.
Okay. So when we change it to the algebraic vector and it asks us for the component form, we have to give them the letter where the arrow is, so the tip.
Very good.
Okay, thank you.
You have it exactly. Congratulations. Yeah. Okay. Any other questions while we're here? Aren't vectors fun?
How would we know what's a geometric vector and an algebraic vector?
Also a good question. A geometric vector is not in standard position. Well, how do you know? Well, because it doesn't have its initial point located at the 0, 0 at the origin.
Professor, do we always want to put our vectors in algebraic?
Most of the time, yes. That's our favorite position from now on.
And the initial is here in this case for B4 for A8.
Well, the initial point is A, because they told us the vector is AB, and the very first uppercase letter is understood to be your initial point.
Oh, okay.
And the
Okay.
second letter, order matters. The second letter is understood to be the terminal point, the one that has the tip, the arrow.
Okay. Thank you.
Sure. Okay, let's do equality of vectors. Now, this little definition is going to seem like Captain Obvious, and you'll probably overlook it and go, oh yeah, it makes sense, boring. But it's going to come and save us on multiple occasions. So I'm going to put stars by it because it's going to come to the rescue in 2 problems in this lecture. And if I don't finish today, for sure by Wednesday, okay? So, and I'll let you know when it's coming to save us. Don't worry. I'll go to the rescue. Equality of vectors. Yay. So what does it say? It says a vector U that has the component form U1, U2, and another vector V with components V1, V2 are considered equal if and only if their scalar components match. So the U1 had better be equal to the V1. Okay. And the U2 had better be equal to the V2. Okay, and they're equal. Now, again, this seems like, well, of course. I mean, if you had a vector U with components 2, -1, and you had another vector V with components 2, -1, I hope you can agree that the scalar components match, so these vectors are equal. Of course. So that's why I say it seems really obvious. So how is that helpful? Don't worry, it's going to rescue us later. Let's do some vector operations. In other words, adding 2 vectors together, as well as something called scalar multiplication. What the heck? Fill in these blanks. And it's what you would expect too, folks. It's what you would expect. There's nothing mysterious about this definition that you will see. So here we go. Let's have a couple of vectors, U and V. And they're going to be vectors in the plane. What does that mean again?
2D.
2D, good. 2D, yeah. And let's see be some scalar. What's a scalar? Just some pure real number like 17 or 4.2 or -57. I don't know, whatever. It's a scalar. Let's say you were trying to add U and V together. And you already have their component form, which means they're automatically in standard position because you have the component form. And somebody says, hey, can you add U and V together, please? And you're like, yeah, sure. So you're going to take the component form for the U vector and then plus the component form for the V vector. And what the heck is the result? Well, I do claim the result is a vector. So you are going to want to use the angular brackets. So you're going to go bracket, bracket, leave some room in there. And you're going to have 2 scalars separated by a comma, okay? The first scalar is going to be the sum of what I call the X components of your vector. So the U1 is the X component for the U vector, and the V1 is the X component for the V vector. Just add them together. And then comma, U2 plus V2, and we're done. It's that simple to add 2 vectors together when you have standard position component form. Okay, what about a scalar multiple of a vector? So what if somebody gives you the vector V, but they want you to multiply it by some number C, which could be positive or negative. So the intermediate step will be, you'll have the C sort of sitting outside the vector, fine. Then what? You can think of distributing the C and making it hit each of the components inside your vector, and you're done. And so the scalar multiple of a vector is still a vector. What about the opposite of a vector, which is also known as the negative of a vector? What's that? Who cares? Well, you do, because a lot of times you want to go in the opposite direction of a vector, and it's really easy to get there. you just turn 180 degrees and you put a negative sign in front of it. So negative v, which is the opposite of this component form, and negative is just the same as the scalar -1. So you just distribute it. And so the new components are simply opposite in sign. Easy peasy. What if somebody wants you to subtract two vectors? And remember, with subtraction, with real numbers, order matters. And it does also with vectors. So if you were going to do u minus v, that's going to give you a different result than v minus u. So be careful. But u minus v, what is it? There's u minus v. You're going to get a vector, so do your angular brackets. And then you're going to go u1 minus v1, comma, u2 minus v2, and we're done. Now, there's one student who mentioned that they are in linear algebra right now, or if you've taken linear algebra already and you didn't answer my question, I want to say something about the textbook we use here at Southwestern and some issues. In the linear algebra text, Math 254, they don't denote their vectors with angular brackets. They use parentheses instead. And I'm not going to allow that in this class. Why not, if the linear algebra folks are doing it? Because it's confusing. Well, why is it confusing? Because in this class, the parentheses are going to be used to represent points. So like if somebody wanted the point 2, 3, so let me just, find the point 2, 3 right here. The point 2, 3 is denoted with parentheses, with the ordered pair, okay? And that's very different from a vector. So the vector with components 2, 3, that would be in standard position, it would look like this. We'll call this vector v. You would use angular brackets with the 2, 3. That's very different from just a dot, a point. And so I am very much a stickler for sticking to that representation in our class. Component form for vector uses the angular brackets so that we don't get confused with vectors and points. Because and it's going to matter on your quizzes too. If you meant to say a point and you didn't use the parentheses, you started using brackets where it was points or vice versa, I'm sorry, but I'm going to have to take a point off every time you're not being true to what it is, okay? It's not that hard to learn. Okay, now let's look at some geometric perspectives of vector addition as well as subtraction and scalar multiplication. When I ask you to add two vectors, typically I'm not going to have you graph them very often, once in a while. But if you're in physics, you really have to know visually what these look like because they use a lot of vectors. So take a look. When you do vector addition, there's two ways you can think of it, and both are fine. It just depends on what's the more common way to think about it. And I'll tell you which one of these methods is the more common way in a moment, but not yet. So suppose you had a vector u that was over here. There he is. And say you had some other vector v over here, hanging out in space way over there. And somebody said, hey, I want you to add those two vectors together. So what you're going to do is you're going to translate one of the vectors. And remember, we're going to translate v, which means move them around. Remember that once you have a vector, it represents infinity vectors, as long as you maintain the integrity of it. You maintain the direction and the length. So I'm just going to copy you down again. He's still kind of lying flat on the ground. V, I'm going to translate him so that his tail is on the tip of u. So here's V. We just moved him so that his initial point is right on top of the terminal point of u. That's called the tail to tip method. Well, then what? Well, the vector u plus v is the vector connecting the tail of u to the tip of v. That's this vector right here, u plus v. And that's called the tail to tip method. And there's a picture of what u plus v looks like. All right, let's do the same u plus v. So here's the same u right here. Oops, I can't draw a straight line this morning. U. And let's say V is still over here. Okay, fine. Add those two guys together again. Well, I'm going to translate V again, but in a different way. I'm going to copy down U. He's still lying flat on the ground. Fine. V, I'm going to move V where his tail is right on top of the tail that U has. So their tails are touching. I'm going to maintain the integrity of V. He's still pointing in the same direction and he still has the same magnitude, length. Well, now what? Well, can you imagine that these two vectors are adjacent side lengths of a parallelogram? I hope you can see it because I'm going to draw in what the other two sides would look like. Can you guys visualize that parallelogram right there now? I hope you can see it. Well, yeah, so what? Well, the diagonal of this brand new parallelogram is the sum, U plus V. That's the diagonal of the parallelogram. And I hope you see that both of these U plus V's are essentially the same. Well, which one's better? They're both the same. Which way is better? They're both fine, but I just want to tell you, if you do take a vector calculus class, which comes after this one, and we don't offer it here, you'd have to go to San Diego State and take Math 532, and you see, I think you'd take Math 2D, D as in dog, and that'll be vector calculus. They'll most likely talk about the parallelogram law. That's the most commonly referred to when you're adding vectors together. Just so you know, that's what it looks like visually. Now, what about vector subtraction? What the heck? What if you subtract two vectors? So here's U, here's V. If I translate V so that their tails touch, the vector U minus V is the vector connecting their two tips. Oops, I'm not doing a good job. Okay, that is U minus V. Well, what about V minus U? That's a different animal. Here's U, here's V again. V minus U would also be connecting their tips, but it would be pointing toward the tip of V instead. So this vector here is V minus U. Well, since you guys know that subtraction can be written as adding a negative, I hope you would agree that U minus V is the same as U plus negative V. So if we use the parallelogram law instead, so here's U, negative V would be pointing in the opposite direction. If V is pointing that way, negative V would be pointing, keep the same length, but pointing in that direction. And if we use the parallelogram law, try to imagine these two vectors as adjacent side lengths of a parallelogram, then the diagonal would be U plus negative V. U plus negative V, which is the same as U minus V. So this vector and this vector are the same. They're both pointing a little bit down and to the right, and they have the same magnitude. So U minus V, same as U plus negative V. Okay, and we're done with vector subtraction. Now, what about scalar multiplication? What of it? It's cool because it allows you to stretch or shrink a vector. So let's go back in standard position. Here's the x-axis, here's the y-axis. Suppose you had a vector, I don't know, just any vector here. How about U? There he is. And somebody said, I want you to multiply U with a scalar rather. What if I said 2U? What does 2U look like? Well, you're doubling U essentially. So 2U is going to be pointing in the same direction as U, but it'll be twice as long. That's all. Well, what about, oops, no, I don't want to do that. What about like 1/2 U? 1/2 is a scalar. Sure. Well, 1/2 U would simply be a vector pointing in the same direction as the original U, but only half the magnitude. So we shrunk him a little bit. And you can use negative scalars too. What if I said negative 1/2 u? Well, it would be half the magnitude, but pointing in the opposite direction. So it'd be pointing that way, and we'd have negative 1/2 u. So scalars can be positive or negative. Okay. And that is a nice visual on adding, subtracting, and scalar multiplication. How are we doing?
Professor, could you maybe explain it once again, the scalar multiplication just a bit?
Sure.
Please.
Scalar multiplication is stretching or shrinking a vector. You multiply it with a pure number because a scalar is a pure number. And you'll either stretch it if it's a scalar that's greater than 1, like the doubling, or you'll shrink it if it's a scalar between 0 and 1. That's all. Let's do some examples. Okay, so I'm going to do this example where you're going to be looking at scalar multiplication as well as addition and subtraction, and sometimes all in the same problem. Can you do that? Can you do scalar multiplication with addition and subtraction all in the same problem? Sure, it's totally legal. So let's look at some examples with actual numbers. So hopefully this will clear up any confusion you still might have regarding anything we just covered. So in this example, they're giving us two lovely vectors in component form. Yay. And we're going to find the following and write our results in component form, because our results are also going to be a vector. So letter A, 2/3 u. This is scalar multiplication right here. This is an example where we're multiplying u with the scalar. Scalar is a pure number, 2/3. So how do we do that? Very carefully. I'll do an intermediate step. You're going to take 2/3 and multiply it with this vector. And you can kind of think of the 2/3 as distributing. So you're going to have 2/3 times -3 and 2/3 times -8. And then clean these up. I mean, just do a little bit of reducing if it's able to be reduced to lowest terms. So the first one after reducing, we get -2. And the second term there, can't really reduce it. So it's just going to be -16/3. And I prefer improper fractions rather than decimals. So unless I start doing a problem with decimals, don't give me decimals. That's sort of an unwritten rule in my class, but I'm telling you in advance. So please write it as -16/3 and not like -5 point whatever. Okay, that's scalar multiplication. Now visually what happened, if you were to graph the u vector, you would simply find -3 on the x-axis and -8 on the y-axis, and then find the point -3, 8, and then draw this vector in standard position. There's u. And the new vector, which occurred when we multiplied u with 2/3, if you graph -2 and -16/3, you find the x coordinate is -2 and you find the y coordinate -16/3. I claim it would be pointing in the same direction as u, but it would be about, it's 2/3 in magnitude, 2/3 of the length. And that's it. That's scalar multiplication. Does that help?
Yes, it does.
Great. Okay, in letter B, they're doing some subtraction. Woo, let's do it in slow motion. First, you're going to take the vector v, which in component form is angular brackets 825, and you'll subtract the other vector u with components -3 and -8, and you're going to get a vector. So I'm going to leave some room here. You're simply going to take the difference of the x components, so 8 minus a -3, comma, 25 minus a -8, and then do the arithmetic. So your final answer looks like it's going to be 11 and 33. Boom, and we're done. So there is the result of scalar, or excuse me, vector subtraction. It's going to be a vector. And now letter C involves scalar multiplication as well as vector addition. And you want to do the scalar multiplication first, followed by the vector addition. So what I'm going to do right now is I'm going to put everybody in the room in a breakout. I'm going to put you in pairs, and you're going to try this with your buddy. And I'm going to encourage you to turn your mic on so you can talk to your buddy. And everybody is going to do letter C right now, okay? Let's see here. Okay, I'm going to open all the rooms, and once I open them, please go in there, and I'll be coming around and meeting with you too, okay, just to see how you're doing. All right, try letter C. Good luck. Marina, are you here? There she is.
Professor, you're muted. Professor, you are muted.
Professor, you're muted.
I see that now. Thanks, guys. Ugh, I don't know why it muted me for no reason. I didn't mute myself. It just did it. Okay. I'm hoping that you guys got this scalar multiplication and vector addition. So let's just go through this quickly to see if you are on task. Just like in math, regular algebra, PEMDAS, multiplication always comes before addition. So you definitely want to do the scalar multiplication first. So if I did this in slow motion, and I'm going to do it in really slow motion, you're going to have 2 multiplied by angular brackets, -3, -8, plus 5 angular brackets, 8, 25, like that. And I'm running out of room here. Oops. Then you're going to distribute the scalar. So you're going to have like 2 times -3, and I'll just do the multiplication quickly here. So the scalar multiple there of 2 with the u is going to be that vector with -6 and -16 as components. And then when I distribute this 5, woo, I'm going to get 40. Oh, crap. What's 5 times 25? 125. Okay. So that's an intermediate step. And now when you sum up 2 vectors, you're going to get a vector. So I'm going to put my angular brackets, and then I add the x components together, and then a comma, and then I add the y components together. And then I finish by actually doing arithmetic, which sometimes I can screw up with if I'm not careful. And that's why I encourage you to use a calculator to triple check yourself. And there's your final answer. Did everybody get that?
Yeah.
Yay! Success! Well, congratulations to all if you did get it. If you didn't get it, don't be too hard on yourself. You're just learning how to do vectors. Okay? I hear that. So I'm going to do the rest of this page, and then we'll finish out. Okay? And I guess next time I'll start with, I was hoping to get a little bit further, but you know, what can you do? So we'll go for a little bit longer here.
Professor,
Yes.
sorry, are we going to do number D?
Yeah, we're gonna
Letter
do
D?
it now, but I need more room. So what I'm
Okay, sorry.
no worries. Yeah, but sometimes I accidentally skip stuff. So thank you for making me honest here. I'm going to append a page because I didn't give myself enough room, and you probably need more room also. And that's why the back side of your course reader, you'll notice when you finally purchase it, has blanks so you can continue writing. Okay, this is a typical problem you'd see in a linear algebra class, but I think it's important enough where this will be on quiz 1. But I will change the numbers. Okay, I'm telling you, well, and the previous problem is going to be on quiz 1 also. So know how to do that, the A, B, and C. So how does this operate here? They're giving you a vector W. They're giving it to you. Like, there's W. Okay, fine. And you already know what U and V are because they gave you U and V already. Okay, so you know all 3 vectors. So what do they want? They want you to find 2 scalars, pure numbers, A and B, such that you can write W as a linear combination of the vectors u and v. What the heck does that even mean? It means that W can be written as some pure number A times U plus some other pure number B times V. So what do they want? The final answer, once we're done, is you have to say what is A and what is B. Those are the mystery numbers. So find the mystery numbers. Now, when I say that this kind of thing is done in linear algebra all the time, when I teach linear algebra, I'm not teaching it this semester, this is something I ask my students to do all the time. So I'm giving you a leg up in your linear algebra class. So writing a vector as a linear combination of other vectors. Okay, so what? So I'm going to do the intermediate step here, all the intermediate steps. So when they say W is equal to AU plus BV, I'm going to just fill in what I know. I know that W in component form is that. I don't know what A is. It's a mystery, but I do know it is a pure number. I just don't know what the pure number is. Oops. And then B is some scalar pure number. I don't know what he is either. So this is an intermediate step. So just go with me because this will make sense. You have all the tools to do this problem. You do. Because when you solve a linear system, which is what's going to happen here shortly, you learn how to solve linear systems in your algebra class like 2 years ago. Okay, I'm going to do the scalar multiplication because I'm supposed to. So let's do that. That's our next step. So this, when I distribute the A, the first component will be -3 times A, comma. The second component, -8 times A. And then when I distribute my B scalar, I'll have 8B, comma, 25B. Well, now what? Don't worry, we got to go slow here. Let's add the right-hand side vectors together because that has to be a single big old vector. So the X component will simply be the sum of the X components of the vector here, comma. And the Y component will be the sum of the Y components. And the left-hand side hasn't changed. I'm just going to copy it down. Okay, now, this is the key. Remember when I said equality of vectors, even though it seems very, very obvious, is going to save us on occasion? It is now going to save us. We need it. Well, how is it going to be helping us? Well, I claim we have an equation where one vector on the left-hand side, it has to be equal to the vector on the right-hand side. This vector has to equal this vector. So by equality of vectors, what needs to be true? What needs to be true is the 14, that component has to be the same as the X component of the right-hand side vector, -3A plus 8B. And similarly, the 41 had better be equal to -8A plus 25B. And folks, this is a linear system of equations. There's 2 equations and 2 unknowns. And you learned how to solve this in an algebra class. Now, there's different ways to solve it, of course. One way would be to use the substitution method. That would work. I'm going to use the elimination method. So if you don't mind, I'm going to multiply the top equation by both sides by 8. Okay. And I'm going to multiply the bottom equation by, because I want to add these 2 guys together is what my plan is. I'm going to multiply the bottom by -3, both sides. So 8 times 14 is what? 112. And then when I have 8 over here, I've got -24A plus 64B. Yeah, I can't talk right now, sorry. Don't know. Did not tell me.
I don't know what kind of quiz it was.
Okay, and then what? I think, did I do all that multiplication right? Stop me if you see me do a mistake, okay? Speak up. So what is 112 minus 123. Quick. Negative 11. Here I get 0. What's 64 minus 75? Quick. Negative 11b. Ah, this will be easy to get b. b is going to be just negative 11 over negative 11, right? Everybody with me? So what does that mean? B is equal to 1. Ah, I got one of the unknowns. Now what? Well, I need to get another unknown. How about if we substitute b equals 1 into this equation or the original? How about if I do the original where it's negative 3a plus 8b equals 14? If I substitute b equals 1 in this original equation here, I should be able to get the a, right? What if I subtract 6 from both sides, and then a is equal to negative 2. So final answer, a is negative 2 and b is 1. And those are the mystery scalars that will enable us to write w as a linear combination of the other two vectors, u and v. So what has to be true right now? W has to be negative 2 times the u vector plus 1, that's the b, times the v vector. This has to be true. And it is. You can double check it. Okay? So this was a multi-step problem that took a little longer than 2 minutes to solve, but it uses all of your knowledge that we just went over. Vector addition, scalar multiplication, and then solving a system of 2 equations and 2 unknowns from your algebra days, okay? So let's do a theorem of properties of vector operations, and then we'll wrap this up for today. And on Wednesday, we'll pick up learning how to unitize a vector, writing a vector as a standard with the standard unit vectors, and more, okay? So we'll be resolving a vector into its components next time too. Okay, fun stuff. So this theorem is just more obvious things. You may think it's pretty obvious. Although if you go take a vector calculus class, they might make you prove these, just so you know. So suppose somebody gave you vectors in the plane, that means 2D. And by the way, this theorem will work in 3D also. And let's say C and D are just numbers, they're scalars. So what's true? Well, it doesn't matter what order you add 2 vectors, because you'll still get the same result. Now, that's not true for subtraction. Subtraction order does matter, just like with numbers. 5 minus 2 is not equal to 2 minus 5, but 5 plus 2 is equal to 2 plus 5. So you have commutativity as long as you're adding, fine. What if you have 3 vectors and you're trying to add them together? Well, you could add the u and v together and then w, and that'd be fine. Or if you prefer, you could add the v and the w together and then add u. Either way, it doesn't matter. Same thing, because we have associativity. What about the 0 vector? If you add him to any vector, it's just like adding the number 0, you'll still just get the vector. What if you take a vector and add his opposite? You'll get the 0 vector. And make sure you put a little arrow on top, because if the answer is 0 with a vector on, it's a 0 vector, but you just write 0 on your paper, I'm going to have to take away a point or more for bad notation, because the pure number 0 is very different from vector 0. Okay, what if you have 2 scalars that you're trying to multiply a vector with? And you want to first do one scalar and then hit it with the other? Fine. Or you can multiply the 2 scalars together and then multiply it with the vector. It doesn't matter. What if you have the sum of 2 scalars that you're multiplying with a vector? You could do it like that. That'll work. Or you can distribute if it helps make the problem easier. Legal. Similarly, you can distribute a scalar over the sum if that makes it easier. Or you could just add the vectors together first and then hit it with the scalar multiplication. If the scalar is 1 and you're doing scalar multiplication, well, 1 times anything is just the anything. That's the multiplicative identity. And 0 times a vector will be the 0 vector. So if your scalar multiplication involves the number 0, then you'll always just get the 0 vector. Not very interesting. Okay. Woo! And